Welcome to qnawire.
Over here, we're going to have the two following reactions. One is going to be the a reaction that is going to be through the benzene mechanism. We're going to generate a benzene intermediary, and on the other one, this is going to correspond to a Birch reduction. So, for the first case, what we're going to have is that initially, what is going to occur is that the NH2 negative is going to take away one of the hydrogens that we're going to have on our benzene ring, and the pair of electrons will go to generate our benzene intermediate. When we do this, the Br is going to be taken away by this substitution. So what we're going to get is an intermediary that is going to contain a triple bond over here. We're going to have our CF3 on this position. And now we're going to have two different options. We can have an attack over here or over here. Both of the attacks are going to be valid and they are both going to occur by the NH3. So what is going to happen? Well, let's consider the two options. Over here, I'm going to write down the mechanism for attack on position A. And to the right, I'm going to write down the mechanism for attack on position B. So what is going to happen is that through the route through mechanism A, the NH3 is going to attack over here. This is going to generate a negative charge on the other position. Let's write this down as NH2, and I'm going to write down an hydrogen over here. Okay, we're going to have this CF3 that, as I mentioned, is going to be an electron withdrawing group, and we're going to have a negative charge on this position and the double bond. Now, this pair of electrons corresponding to the negative charge is going to take away this extra hydrogen, and the pair is going to go back here, generating the desired product. Of course, over here, we need to add the other double bonds on our benzene ring. This would generate the corresponding NH2 in the para position. Now, why this attack is going to be preferred, let's look at what is going to happen over at position B. The intermediate that is going to be generated is going to have a negative charge on this position upon attack, and the NH2H with the positive charge over here. So what is going to happen? Since we have an electron withdrawing group, the negative charge is favored when it is closer. So over here, as you can see, the negative charge is going to be on the para position with respect to the electron withdrawing group, and on this route, it is going to be on the meta position. So, since in this route, the negative charge is farther away from the electron withdrawing group, this pathway is going to be destabilized and the reaction is not going to proceed through an attack at position B. The correct mechanism is going to be the attack at A, generating this product with high stereoselectivity as mentioned. So now, since we can go ahead and provide the reasoning for the Birch reaction. So if you want, you can pause the video at this point just for you to review the reaction mechanism, and I'm going to proceed with erasing everything. So the next reaction mechanism, what is going to happen is, while I'm erasing everything, is that we're going to have an OH group, and remember that the OH is going to be an electron donating group. So in the case of the Birch reduction, what is going to occur is that when we have sodium and NH3, we're going to have a redox reaction in which we're going to generate sodium plus a solvated electron. And this electron can attack different parts of the benzene ring, and in general, the movement of electrons is going to look as follows. Let's say that we have our benzene ring, like the most generic way of writing down. So, one pair of electrons, let me act like my them in such a way that it's going to be easier to look at. We're going to have these pair of electrons are going to get together. We're going to generate over here a movement to this position. And finally, over here, we're going to have a split. These half arrows correspond to moving just a single electron, okay? Normally, when we draw the full arrow, it is going to mean that we are moving a pair of electrons. Over here, we're moving single electrons from one position to another. And what this is going to generate is going to be a benzene radical ion, which is going to look like as follows. As you see, now the double bond is going to be contained on this position and on this position, and we lost the other two double bonds to an hydrogen here, the dot, with this going to be a radical, and the other hydrogen with a negative charge on this position. So this is going to be the benzene radical ion that is going to be generated. Notice that through this reaction mechanism, what is going to occur is that we're going to generate this negative charge on this position. So what needs to happen? Well, think that instead of having a nitrogen, I have any electron donating group. What is going to occur is that the electron donating group is going to donate electrons to this part and is going to destabilize destabilizes the negative charge on that position. So for that reason, and let me do the example directly with the OH group that we're going to have, we have this couple of pair of electrons of the oxygen, and the donation of that pair of electrons towards the benzene ring is going to have a destabilizing effect. So for that reason, the only possible position for the electron donating group to appear at is going to be away from the negative charge and closer to the radical on the other side. Over here, we're no longer going to have this destabilizing effect, and the product is given essentially by electron repulsion. Is going to determine the product. So over here, we can write down also the OH on this position, just to keep everything extra consistent. So after this happens, we can follow with the normal reaction mechanism. We have identified how to generate the correct intermediate, the correct benzene radical ion. So we're going to continue from this point onwards. As we mentioned, we are going to have only two double bonds over here. We're going to have our hydrogen with the radical electron on that position, and our OH group over here, with the pair of electrons corresponding to the negative charge over there. So the first step is going to be that the pair of electrons of this anion is going to attack one of the hydrogens in ethanol that we're going to have. This pair of electrons is going to move, generating the following species, in which we're going to have now two hydrogen atoms over here. Here we have our single hydrogen with the electron that we're going to get, and after this has occurred, one extra electron coming from the reduction of coming from the oxidation of sodium is going to participate with a half arrow over here, Remember, half arrows are for movement of a single electron, which is going to produce an ion that we're going to employ. So now we are getting at closer to the desired product, our OH group here. Now I'm going to meet the two hydrogens on the other side, and over here we're going to have the hydrogen and the pair of electrons with a negative charge. So again, now this pair of electrons is going to attack one of the hydrogens of the ethanol, and with this we are going to be done. Remember that the ethanoate ion that is going to be generated is going to be neutralized with sodium, so essentially we're going to get sodium ethanoate on each of the steps. So with this, we're going to produce our final product, which would be double bond here, OH, plus this another equivalent of sodium ethanoate. And with that, it would be all. Now the two hydrogens have been added on each of the positions, and we're done. Let me just make this benzene ring a little bit prettier because it looks kind of bad. So double bond here and double bond here. And with that, we're done. Thank you very much and have a good one.